Okay, today we're going to start our unit on vectors. Now, as always, before we start any unit, we need to do some basic definitions and terminology to help us understand. So, vectors are very useful in a lot of different fields of study. For example, to describe the displacement of an object, two numbers are required, the magnitude and the direction of the displacement. To describe velocity of a moving object, we also need two numbers. We need the speed of the object and the direction of travel. Quantities such as displacement, velocity, acceleration, and force, they all involve two main things: magnitude as well as direction. And these quantities that involve magnitude and direction are called directed quantities. And there are different ways to represent directed quantities. One way to represent directed quantities in mathematics is through the use of vectors, hence our study of vectors. So what is a vector? A vector in a plane is a line segment with an assigned direction denoted by the arrow that you draw above the segment. So if this line segment AB, that's the vector, we'd call this vector AB. And the length of the line segment, which is called the magnitude of the vector. So the length of the line segment is the magnitude. And our notation for magnitude looks like the absolute value of vector AB or the double bar vector AB. So I will use the second notation. Okay, use the distance formula to find your magnitude. Remember from geometry class, our distance formula of given 2 points is the square root of our x of our second point minus the x of our first point, quantity squared, plus the y of our second point minus the y of our first point, quantity squared. To find the magnitude of vectors on a coordinate plane. The arrow represents the direction of the vector. So if vector x is represented by the point P, which is x1, y1, and point Q, which is x2, y2, then the component form of the vector, which is represented by these arrowed kind of brackets, is x2 minus x1 is our x component of a vector, y2 minus y1 is our y component of a vector. This is called component form of a vector. So in this next few examples, we're going to see how well you use the definition, magnitude, and direction to answer the following questions. So what is the magnitude and direction of vector AB? So remember, magnitude is another thing for the length of the line segment. So that means our magnitude of vector AB is equal to 8.5. Now, the direction is the angle from the positive x-axis in standard position. So it's angle always in standard position. So this direction would be 28 degrees. Now, we're looking at vector RT. Its magnitude is 4.5. But the direction is not 110 degrees because direction, it's very, very important. The direction is measured from a standard position. So to find our direction, I take 360 minus the 110 degrees to get that vector RT's direction is 250 degrees. Okay, your turn. Try the magnitude and vector of vector JK. The magnitude of vector JK is 12. The direction of vector JK is 360 degrees minus 70, or 290 degrees. Okay, now what if we don't have the graph? We actually have to calculate the magnitude. So we're going to graph each of these, and then we're going to find the component form, and then we're going to find the magnitude. Okay, so first you graph your initial point, which is the R. Then you plot your terminal point, which is the S, the -1, -10. And then we draw a vector starting at point R, ending at point S. And we have a little arrow there. So that's our vector. Now, I went a little past point R. That should not happen, so you'll need to fix that. Okay, now we're asked to find the component form of this vector. So remember, the component form of the vector is those funky little angular braces. And so we have our component form. Now we take our x2, our x of our terminal point, so that would be s of the x for the s point, minus the x for the r point. And then we take the y of our terminal point minus the y of our initial point. And that's how you find component form. So in this example, to find our component form, I would take our terminal side, which is our s, and the x value of the s would be -1, minus a 7, comma, -10, minus 2. And so our component form of vector rs is -8, comma, -12. Then you are asked, now before I go farther, what is component form? What is that telling us? Well, basically, component form is taking this vector and sliding it over so that the initial side starts at the origin, 0, 0, the graph. So if I plot this point -8, -12 on the graph over here, and then I draw a ray from that from the origin to that point. Notice this vector here has the same length, same magnitude as the vector rs, and it's going in the same direction. So this has the same magnitude and direction as the given vector. It just makes it easier to work with if we can convert it into component form. And so that's what component form tells us. Now, we were asked to find the magnitude of this. So I'm going to first find the magnitude like we learned in the last section, last example. But there is another way to find your vectors. You could also took your component form and do the x-coordinate of your component form squared, which is -8 squared, which gives us our 64, plus our y component of our vector, which is -12, quantity squared, which will give us 144. So you can use the formula, the distance formula, or you can use x component squared plus y component squared and take the square root of that. All right, so you try this, your turn problem. Here's my point P, and then up here is my point Q. And so my vector starts at P, goes to Q, no arrow shows the direction, you must draw the arrow. And so that's my graph of vector PQ. Now, to find our component form of vector PQ, I take my terminal x, which is our -5, minus our terminal y, which will be -4, so that becomes +4, and our terminal initial y, and then our terminal y minus our initial y, and we get component form of -1, comma, 12. Now, to find our magnitude, I can do the distance formula, and that's what I'll write down, but remember there is another way to find it, since we already found the component form. Okay, so if I use the distance formula to find my magnitude here, that would give us -5 plus 4. Wait, that is the x component that's the x value of my component form. And then to get my y value, that'd end up with 2 plus 10. Well, I just did that. That was our y component. So I could skip this step above and go straight to my x component of my, the x component in the component form squared, plus my y component in my component form squared, which will give us 1 plus 144, which is 145. And if that simplify down, you do, but this one does not simplify down, so that is my magnitude. Okay, two vectors are equivalent if they have the same direction and magnitude. Okay, for vector A, let's see if vector RS is equivalent to vector PQ, or vector U is equivalent to vector V. So vector RS or vector V, magnitude, because remember, to be equivalent, they must have the same magnitude and the same direction. So to find our magnitude here, I'm going to take my terminal minus my initial of the x and do the same thing with the y, square those, and then add them, and then square root, and I get the square root of 13 as my as this. Now, for vector PQ, you'll notice that I could take my terminal minus my initial plus my terminal. My initial is the 0.00. So this is actually a component vector. And so I could have just did 3 squared plus 2 squared gives us square root of 13. So they have the same magnitude. Now we got to figure out they have the same direction. So all these two lines slanted the same. Well, how do you find slanted on a line segment? Well, you find the slope. So we can find the slope of vector v. Remember, slope is y2 minus y1 divided by x2 minus x1. And so for vector v, that would be a slope of 2/3. And then I can find my slope for vector u, which is y2 minus y1 over x2 minus x1, which gives us the same slope. So I can say vector u and vector v are equivalent vectors. All right, you try the next one. To show that these two vectors are, vector v and vector u are equivalent vectors, I must first find the magnitude of vector v, which is the square root of 10. Then I need to find the magnitude of vector u, which is also the square root of 10. So I passed the first test. So then I need to find the slope of vector u and the slope of vector v. Now, there is another way that you could have proved that these two vectors are congruent, are equal to each other, because component vectors are equal to the initial vector. So since our vector u has an initial point at 0, 0, it's possible it's a component vector. So vector u is represented by the component vector of 3, 1. So if you rewrote vector v into component form and you got 3, 1 as its component form, then you would also prove that these two vectors are are equal. So those are two ways to find equivalent vectors. So now that we know how to find, and now we know some little bit about vectors, let's talk about some vector operations. So I'm defining vector u and v as this above, and k is just a scalar. That means a number. And so if I want to take vector u plus vector v, I take the x-coordinate of vector u plus the x-coordinate of vector v, comma, the y-coordinate of vector u plus the y-coordinate of vector v, or the second coordinate. And then that would be my answer. So if I wanted to multiply by a number times a vector, I can just distribute that vector to each component of the vector. So that would be v times u1, comma, v times u2. Now, if I want to negate a vector, do the opposite vector, go in the opposite direction, okay, that would just change each of my components of my vector. So that becomes negative u and u sub 1 and negative u sub 2, or v sub 1 and v sub 2. Now, if I want to find the difference of two vectors, I'm just going to take the x component of the first vector minus the x component of the second vector, and the y component of the first vector minus the y component of the second vector. Now here's some illustration of what some of those operations look like. So here's my basic vector. Vector v is this first vector here. Now, if I want to take half of vector v, it would be half its magnitude, so it'd have half its length, but in the same direction. If I want to take 2 times vector v, notice that this will be in the same direction, but it has double the length of the original vector. If I want to take negative vector v, that's the same length of vector v, but going in the opposite direction. And negative 2/3 vector v is this going in the opposite direction of the given vector, but 2/3 as long. All right, let's do some operations here. So here is my vector u and my vector w, and I want to find 2 times vector v, so that takes 2 times the x component vector v, and then 2 times the y component vector v. So I'm just distributing that 2 into my vector, and so I get the component form of negative 4, 10. Now if I take vector w minus vector v, so it takes the x component of our w vector minus our x component of our v vector, and then our y component of our w vector minus our y component of our v vector to get our vector 5, negative 1. Okay, you try the next one. Okay, one way to show your work here is just replace that vector v with its component form. Replace that vector w with its component form. Now the problem with this one is order of operations. We must do multiplication before we do adding and subtraction. So you have to distribute the 2 into your second vector first, then you can add your 2 vectors together. So did you do your order of operations correct? So you should get that this is vector 4, 13. In many applications of vectors, it's useful to find something called the unit vector. So the unit vector has the same direction of the given non-zero vector v, but it only has a magnitude of 1. So we do this, we find this unit vector by taking their vector v and dividing by the magnitude of vector v. So we can get a length of 1. So think about the unit circle has a radius 1, same thing here with our unit vectors. So we take our formula for unit vector is our vector divided by our magnitude of the vector. So find the unit vector in the direction of vector v. Here's our formula for unit vector. Now, dividing by the square root of 29 is the same as multiplying by 1 over the square root of 29. So this is scalar multiplication. So I just distribute throughout to each component of my vector. And this is the unit vector of vector v. Now remember, unit vector should have a magnitude of 1. So let's verify that this unit vector has a magnitude of 1. So let's find the magnitude of this vector. So remember, to find the magnitude of a vector written in component form is I take the x component and square it, plus the y component and square it. And that will give me 4 over 29 plus 25 over 29. And adding those two fractions together, I get the square root of 29 over 29, which is the square root of 1, which equals 1. So yes, my unit vector is 1, has a magnitude of 1. Okay, you try this one. This one has a typo. I think I corrected it on yours. It should just read find the unit vector of v. Okay, to find the unit vector of v, remember you take the given vector and divide by the magnitude of that vector. And remember, our magnitude of a vector in component form is I take the square root of the x component squared plus the y component squared, which will give us the square root of 49 plus 9. And the square root of 49 plus 9 is the square root of 58. So I have the component vector, the vector 7, negative 3 over the square root of 58. So that's multiplied by a scalar 1 over 58. So that becomes the vector 7 over the square root of 58 and negative 3 over the square root of 58. And that is your unit vector for this problem, vector v. The last form we're going to learn is called the linear combination of the standard unit vector. So unit vectors are 1, 0 and 0, 1. These are called standard unit vectors. We have a symbol that denotes these because we're used so often. Instead of writing the vector 1, 0, we'll write I. Vector I is denoted by the vector 1, 0, and vector J is our symbol for the vector 0, 1. So if I wanted to write the linear combinations of I and J for vector A, B, which is written in component form, that would simply be AI plus BJ. Now let me prove to you that this works. So let's start with the right-hand side. So we have that AI plus BJ is equal, and number I is representing the vector 0, 1, and J represents the vector 0, 0, 1. And so distributing the A, I get A0, 0B. Adding those two vectors together, I get AB, which is our original vector. Okay, so we're going to rewrite vector U, 5, negative 7, as a linear combination of I and J. So that's just going to be 5A minus 7J. You try the next one. It is negative 3 minus 8J. Now we're going to ask to find I'm going to do some operations with this now and write our answer in the linear combination of I and J. There are two methods to do this. One, we can do it just like we did earlier in this section. So if I wanted to find 2 times vector u plus 5 times vector v, I can just do scalar multiplication, distribute the 2 to the first vector, each component of the first vector, and distribute the 5 to each component of the second vector. And then add these two vectors together by adding the x components and then adding the y components to get negative 10 36. Then convert that to I and j form. And so that's negative 10i plus 36j. Method 2 is convert the given vector into linear combination of I and j first, and then do the mathematics. So vector u can be written as 5a plus 3j, and vector v can be written as negative 4i plus 6j. And so this becomes 2 times vector u, replacing that u with 5i plus 3j, plus 5 times vector v, and in place of vector v, write negative 4i plus 6j. Then just get rid of the parentheses by doing the distributive property. And then combining like terms, so adding our I terms together, get negative 10i, add our j terms together to get 36j. Notice you get the same answer. I don't care which method you choose, do whichever one is most easiest for you or makes the most sense for the problem. You try this next one. So 3u minus 4v would be 3 times 3i plus 2j minus 4 times negative 1 plus 6j, negative I plus 6j. And then distributing the 3 to the first parenthesis gives us 9i plus 6j. Distributing the negative 4 to our second parenthesis gives us 4i minus 24j. Adding our i's together gives us 13i. Adding our j's together gives us negative 18j. So our answer would be 13i minus 18j. And that's and then now the last thing we're going to learn is how to find the direction of the angle, finding theta. So if vector u is a unit vector such that theta is an angle in standard position, then the terminal side of vector u lies on the unit circle in the way such that our x is corresponding to our cosine of theta and our y is corresponding to the sine of theta. Or if I did this in combination of I and j, this would be the vector cosine theta I plus sine theta times j. Angle theta is called the direction angle of the vector. Now, remember that tangent of theta is equal to sine over cosine. So I could rewrite this as tangent theta equals y over x, or I can use our reference angle is going to be the angle whose tangent is y over x. Now, I've wrote reference angle here because in order to figure out the actual theta angle, remember you have to identify which quadrant you're in because our inverse tangent limits us only to from negative pi over 2 to pi over 2. So let's do an application of this. Let's find our magnitude and direction of this angle. So magnitude of a component vector, remember we just take our x component plus squared plus our y component squared and take the square root of that answer. So that would give us 4 the square root of 2. Now, direction. This is the new thing. So to find the direction, we're going to take the angle whose tangent, theta, our reference angle is the angle whose tangent is equal to 4 over 4. And so that's the, then identify which quadrant theta is in. So theta, because if I plot 4, 4, I would see that it's in quadrant 1. So our reference angle is actually our given angle. So theta is equal to the angle whose tangent is 1. And I know from my unit circle that that is 45 degrees, or pi over 2. Now, usually in most cases in vectors, we go to degrees as default unless specified otherwise. So we'll use degrees unless specified otherwise in this unit. All right, I want you to try find the magnitude and the direction angle of this example. So our magnitude is going to be 3 squared plus negative 4 squared. Or that's 9 plus 16 is square root of 25, which is equal to 5. So now I need to figure out which quadrant our theta is in. So theta is in quadrant 4. And so I want the angle whose tangent is -3/4. I will use my calculator because this is not on my unit circle. Make sure you're in degree mode. And I get -53.13 degrees. And so, but this is not our directional angle, because remember this negative is going clockwise, and remember our directional angle by definition must be in standard position, so it needs to go counterclockwise. So I can find my direction angle by taking this reference angle the calculator gave me and adding 360 degrees to it. And you end up that our actual directional angle is 306.87. Did you remember to do it in standard position? All right, what about if it's written in component linear component of I and j? Well, just convert that into component form. And so if I rewrite if I want to find the magnitude of -1i plus 8j, that's equal to the magnitude of the component vector -2, 8. And so that's the first component squared plus the second component squared, and taking the square root of that sum, it gives us the square root of 68, or 2 the square root of 17 is our magnitude. Now to find our direction, go back to our component form here, which is -2, 8. And so x is -2 and 8 is y. So once I figure out what quadrant theta is in, and so since I'm -2, 8, our quadrant would be quadrant 2. And so I'm going to find our reference angle. So theta is equal to the angle whose tangent is 8/-2, or the angle whose tangent is -4. Using my calculator, I get that an angle measurement of -75.96 degrees. Okay, but that I need a positive angle in quadrant 2 that has the same measurement. So I take this reference angle and add 180 degrees this time to get my theta. And so -75.96 plus 180 degrees gives us a direction angle of 104.04 degrees. All right, you try this last problem. Start by converting into component form, and then find the magnitude. We'll take the first component squared plus the second component squared, and so the square root of 4, which is 2. So your magnitude is 2. Then identify which quadrant theta is in. Theta is in quadrant 1. So theta is going to be equal to the angle whose tangent is the square root of 3/1. And from my unit circle, I know this is 60 degrees in quadrant 1. So my direction angle is 60.